Hello, pre-calculus honors students. Here's 4.6 and 4.7. First, 4.6 is a very short little section on functions of two variables. If you recall the volume of the cylinder, it's pi r squared h. So now you've got an equation that relates to three ideas: the volume, the radius, and the height. Now, it's hard to make a graph of this in two dimensions since it involves three variables. So what we do is a little trick, and we use a two-dimensional graph. We use a two-dimensional graph, but what we do is create the third variable as another constant we evaluate at various points. So here I've set up a slider. So right now my slider is at 3.5. So this is what happens with volume as a function of radius squared. I used y and x for GeoGebra here. Then h is our third variable, but I can change it over here. And that's what you see all over your text. You see a bunch of diagrams with different graphs going through them to represent that third variable. So here's h equals 0, which turns into a horizontal line, h equals 1, h equals 2, h equals 3, h equals 4, h equals 5. Now this comes into play in what we see in the next section, and that's forming functions from verbal descriptions. Often you start with three or maybe more ideas, and you want to come up with one quantity in terms of one other variable. So here in page 161, number 2, express the area of a triangle, equilateral triangle, as a function of the perimeter P. Well, rather than trying to do it all right away, come up with another variable. Let x be each side of this equilateral triangle. So you can start expressing some ideas here. The area of the triangle is 1/2 base times height. Well, we have a lot of variables we could throw in here. Here's the height, we don't know that yet. And so you'd say area equals 1/2 the base x times the height h. You also can use the perimeter idea. The perimeter is 3x's. So now we actually have four variables. Well, if you remember an equilateral triangle, this is a 60-degree angle. And so this is x over 2. And so going from the short leg to the long leg, we multiply by the square root of 3 and 30, 60, 90. So the height is the square root of 3 times x over 2. So now by putting these two together, you can at least come up with area in terms of one variable. Area is 1/2 x times square root of 3 times x over 2. Maybe you remember this formula. It's this area formula for any equilateral triangle. Square root of 3 over 4 x squared. Still we're not quite there because we don't have area in terms of just the perimeter. Well, from the perimeter formula, x equals p over 3. So you put that in for x. So we have area equals the square root of 3 over 4 times p over 3 squared. Let me clean that up. Square root of 3, p squared over 4 times 9, which is 36. There's your area as a function of perimeter. Now in this next problem, number 22, the point xy is an arbitrary point in the parabola y equals x squared. So we want to do two things with this. Express the distance d from point P to point 01 as a function of the y coordinate of P. So that introduces three variables because you have an x and y coordinate of the point and the distance d. And then we want to also see where does it minimize the distance. So first let's get an idea of the situation from the GeoGebra graph. Here's the y equals x squared, and the point 0, 1 is b. And you can slide along point A here and see various distances. And so first you might say, oh, the vertex is the closest point of approach. Well, that's one away, but clearly we get points closer. Why is this? Well, because this is not the focus. 0, 0 is the vertex, but the focus is more like at 0, 1/4 down here. And we'll study that more when we do parabolas again in conic sections. So let's keep going back and forth here and see where it looks like the distance is minimized. And it looks like it's somewhere 0.866, 0.8663. There, we got that just plain old 0.866. Let's see if that's what we come up with in our final analysis. Now, back to expressing the distance from the point 0, 1 to the point P, and that's going to equal distance D. So we say D equals the distance from the general point P, x, y, to this point A, which is 0, 1. So we use the distance formula, square root of x minus 0 squared plus y minus 1 squared. Distance equals square root of x squared plus y minus 1 squared. And we run into the same problem we have with the other question, that is, we've got 3 unknowns here and can't graph this. It does say just get distance in terms of the y coordinate. But, wouldn't you know, recall, y equals x squared. That's our original formula for the point of the parabola. So we can replace x squared with y. So our distance equals the square root of y plus y minus 1 squared. And if we expand this out, we see we have the square root of a parabola, y squared minus 2y plus 1. Or square root of y squared minus y plus 1. So we've accomplished the first goal. That is getting distance as a function of just the y coordinate. But in part B now, part B, we want to come up with when is the distance minimized, or what is the minimum distance. So let's just make a quick copy of this for the next page. And here we are. Let's get the instructions again. What is the minimum distance D? Well, there's our formula. We want to graph D as a function of y. Well, we've never graphed something like this before, but I think you're going to recognize the shape when we see it on GeoGebra. Here's our graph from GeoGebra, and you can see it's the square root of x squared minus x plus 1. I had to change the variables for the sake of GeoGebra. So distance, where does it get minimized? It looks like it's smallest in here somewhere, a little less than 1, and somewhere between 0 and 1. What kind of shape is this? Well, it's not a parabola. It's the square root of a parabola. Here's the parabola that's inside the radicand. As you can see, it's a parabola. And its axis of symmetry is going to be at a half. If you look at the negative b over 2a here. So there you go, axis of symmetry at a half. There's the parabola. And this actually ends up being a hyperbola, square root of a parabola. And it will have the same minimum where the parabola has a minimum. So we can see it's going to happen when x equals a half. Let's see if that's the coordinate on our point from our other geometry problem. Or actually when x is a half, but actually here when y is a half, because we changed variables over there. So that checks out with this. And now we can get the exact answer on our work. And that goes something like this. So the y coordinate of the axis of symmetry will be at negative b over 2a of this inner function. So that's negative 1 over twice 1, or half. So now we can put in a half in for y. So the distance that will be at its minimum there will be at the square root of a half squared minus a half plus 1. Square root of a quarter minus a half plus 1. So that's the square root of 3/4, or the square root of 3 over 2, which you remember from trig a lot last year is roughly 0.866. So there you go. Flange out.